Welcome to Frontiers. These are our seminar series where we bring top researchers working on cutting edge topics in various fields to do deep dives into their work. Today we have a special session. We have Pranav Guruprasad, who's joining us. He's the founding research engineer at FIG, formerly Medarc, as well as the lead of the MultiNet project at Manifold. And today he'll be presenting MultiNet version 1.0, a major release, a new type of benchmark that addresses some critical gaps with the between the near ceiling performance of um, benchmark of models on frontier models on benchmarks, but their poor transition into real world performance and tasks. So thank you, Pranav. Please take it away.
Yeah, hey everyone, thanks for taking the time to join this. Super excited to talk about how we at both FIG and Manifold are thinking about the next generation of not only multimodal benchmarks, but also models. So yeah, let's dive into it. Oh, cool. Yeah, I'll just give a brief introduction. I think like Sid mentioned, work as a founding engineer at FIG, and I've been leading the MultiNet project at Manifold. It's been a completely open source project and effort for the last year or so. We've had a bunch of incremental results and releases, and V 1.0, like Sid mentioned, has been our biggest release so far. It's kind of been the first iteration of our thesis as a project. And yeah, that's my Twitter handle. If you ever want to like reach out about relevant research, multimodal benchmarks, action models, please reach out. Cool. So the way I kind of like structure this talk is basically we start with an idea of what the failure modes, the specific failure modes of AI benchmarks are today, kind of like categorize them, and also before we dive into how we're addressing these gaps, I also just wanted to briefly share a vision on what we think is the next generation of multimodal models, how you measure progress towards building these models and systems, and how MultiNet kind of like plays an important role in this direction. And then finally, I just want to like briefly go over how we're thinking about the future of AI benchmarking and some of the stuff that we've been working on and we think the field should move towards. Cool. Yeah, I'm going to dive into it, and I think at the end there's going to be a chance for some Q&A. So I'll answer any questions towards the end of the talk. Awesome. So I think a lot of you are familiar with a bunch of benchmarks today. Every single model release from like the big model providers, the open source releases always release their models and systems with benchmark scores. And you must have seen the same names. A lot of these releases, SweBench, MMLU, GPQA, Amy, like all of these, they're great benchmarks. But the way I see it, I think there's four different like primary failure modes, right? So most of these benchmarks are saturated. So they're like every single model release, every single system release is basically incrementally doing better. So like if there's a model that's released with an 89% on say something like GPQA, you'll have a state-of-the-art model a few weeks or months later that does 91%. And it's like getting to the point where some of these are like completely saturated as well. And this kind of like gives you the kind of like a dangerous illusion of their capabilities, right? So your model does really well on, say, the computer science questions in the MMLU dataset. But does it actually do well in production where it's supposed to like debug some of your code based on like specific errors, right? So that's like a major issue with benchmarks today. And you'll see this like time and again with every single model release. And two is, I think, a lot of these benchmarks assess very like niche capabilities. Like so, each of these capabilities are pretty important, but I think there's a lot of value when you have an association of these capabilities and test something that's even more larger and higher value for completing more complex tasks in the real world. So PhD level science questions are great, math questions are great, but these are very isolated and can be solved in a very specific manner. And then three, there's obviously the issue of test set contamination. So if you take one of the most popular like coding benchmarks, SweBench verified, all the different variations, it is based on GitHub issues and associated PRs from I think like 12 different open source Python repositories. So by like inherently these are prone to contamination. Models can be trained on them, and there's also been instances where Quen, there's research which kind of like throws light on these instances where a model like Quen basically kind of outputs exact training examples from benchmarks like GSM 8K, or GPT performs really well on benchmarks before it's cut off, and does really poorly on similar benchmarks after like its knowledge cutoff, right? So this is a major issue as well. And another thing that I kind of touched upon is most of these benchmarks test individual modalities, right? So you have MMLU, one of the most popular ones, and it tests a bunch of domains, but it's only language. And I think there's a lot of value in testing how good these multimodal models are at association of modalities, uh, and I think like that's one area where the benchmarks today are lacking. Cool. So this is kind of like my categorization of the main failure points of benchmarks today. Before I dive into uh, before I kind of like dive into how MultiNet fills this gap, I do want to briefly talk about what the next generation of multimodal models should look like, because I think that also informs not only the failure points of current benchmarks, but also how we want models to progress. Both of these together inform how you want to build the AI benchmarks of the future. Right. So today, multimodal models are really good at perception. Now, they're very good at vision language understanding. Uh, but we, at both Fig and Manifold, I think we realized that true value of these AI systems and models goes beyond just understanding, and kind of lies in autonomously taking actions in these complex multimodal environments, right? So like you have like true economic impact at scale when you're able to automate like long horizon tasks in a bunch of different complex environments, similar to like knowledge work, where you're using a lot of tools, the inputs are of various modalities, and stuff like that. So what does this require? Like, how do you build these systems that can take action? So first, I think you need generalization across domains. You need these models and systems to be really good at a domain like question answering, but they also have to be really good at taking a trajectory of discrete actions. Computer use is a good example of discrete actions where you either click or scroll or type. And then you also need to generalize across modalities. So you have to be good at pure language, pure vision, but also the association of vision and language. And then comes generalization across tasks. So these models and systems have to be really good at VQA, visual question answering, also good at grounding elements in UI, and also computer use tasks. And then finally, generalization across environments. So these AI systems of the future are going to have to complete workflows and actions across various different environments. This can be the web browser, this can be your OS with a good idea of your file system, and it could also just be calling APIs for different tasks, right? So I think this is what comprises like this next generation of multimodal models that goes beyond just perception and goes into action taking. Yeah. So how do you measure progress towards building this kind of like next generation of multimodal models? So you can call it like multimodal action models, right? So I think the first step is you kind of identify the capabilities that this next generation of models should possess, right? So it could be discrete actions, like I mentioned for computer use, continuous actions like you need in robotics, VQA, object grounding, spatial reasoning, tool use. All of these are very important capabilities that these models are going to need not only to perceive their environments, but also like take actions, right? So as a first step, obviously like the end goal of this is to like create data for all of these different capabilities and have a really good benchmark that does the association of all these capabilities. But as a first step, there are existing data sets that can be repurposed or processed or used as proxies to kind of identify how well today's state-of-the-art models do on these capabilities, right? And obviously, not all state-of-the-art models today cannot out of the box work on these different domains, tasks, or modalities. So they need to be adapted to be evaluated, and you need to have like clear evaluation metrics and protocols to fairly assess how these models do out of the box are fine-tuned, and whether there is even a direction towards this next generation of multimodal models, given how models today are being architected. Cool. So that's kind of where MultiNet comes in. So this is kind of all of this was kind of a good motivation for why we started MultiNet and the thesis behind it. So we look at MultiNet as like this one-stop shop to assess all of these capabilities and measure progress towards this next generation of multimodal models. So this is a new kind of benchmark. So MultiNet is one of the largest. It's completely open source and comprehensive benchmark that evaluates these generalization capabilities that I mentioned. Of like state-of-the-art models today, right? So there's obviously like a lot of like categories of state-of-the-art models today. Three important categories that we usually look at is vision language models, vision language action models, and generalist models. So vision language action models are supposed to do really well in robotics tasks, And these generalist models have been trained on a variety of different tasks like vision, language, perception, robotics, computer use. So these are like the three main categories we're looking at. So with MultiNet, I think we offer a complete open source like SDK that allows you to like download, like translate, process, use these evaluation data sets. We also give open source model adaptations that allows you to like basically adapt today's state-of-the-art models to completely out of distribution domains. And we have a curated set of evaluation protocols that you can use, and obviously a submission software that makes it easy for the community to submit any of their models and kind of get an understanding of where they are with respect to this next generation of models. And we've had a lot of artifacts along the way, and you can dive deep into these. Our website is kind of a good place where we have all of our research consolidated. So a lot of research papers, blogs, etc. So please take a look whenever you get the chance if you're interested. I'll go over a couple of couple of our incremental releases before I get into V 1.0, which is our latest and biggest release. So with MultiNet V 0.1, the aim was to assess these three categories of models, right? A state-of-the-art vision language model, a state-of-the-art VLA, and a state-of-the-art generalist model on real-world robotics data. So this falls kind of under the continuous action trajectories capability. And so we evaluated these, and you can like take a dive deeper into this project by going to our website, reading our research paper. But on a high level, that we observed that none of these categories of models have the ability to generalize, even VLAs. So what are VLAs? Vision language action models are basically these models that have VLMs as backbones, and they are co-trained or fine-tuned to do well on specific robotics tasks or a category of robotics tasks. So when we evaluated them on real-world robotics trajectories from the OpenX dataset, you notice that even in like in domain, slightly out of distribution, there is a big gap in generalization capabilities. So all of them do really bad. But some things that came, like a really good result that came out of it was that we were able to adapt a VLM like GPT-4o to actually do robotics tasks by building this sort of like, we have a modular open source framework called Genesis that kind of like adapts GPT to a completely new domain of data, which is robotics. But yeah, big gap in generalizability in robotics. And then with MultiNet V 0.2, we went beyond robotics and we went into the discrete action space capability. So a good proxy for discrete action space is gameplay. So for this iteration of MultiNet, we used the ProcGen dataset, which was an environment that was built by OpenAI. But when you have expert trajectories of agents playing this game, it becomes kind of like this ground truth dataset of discrete action spaces. And so we evaluated how well VLAs and VLMs do on this like completely new domain. And again, I think you noticed that the scores are really bad. We evaluated them using recall scores and Breyer mean absolute errors. Breyer mean absolute errors are a good way to assess the confidence of a model in predicting a certain action class in a discrete action space. And you notice that again, it very poorly generalizes. And an interesting result from V0.2 is that there's a clear action space collapse. So what does that mean? That means that a lot of these models basically predict a certain like one certain action class or a set of action classes irrespective of the inputs, right? So for example, for ProcGen, one action space collapse we noticed was that a specific model always predicted action 4, which is basically the no operation action in ProcGen. So this gives you an idea of how like clueless these models are when you go completely out of distribution, out of domain. And yeah, feel free to like dive deeper into this as well. We have a research paper and it's on our website too. Okay, so now coming to MultiNet V 1.0. I think with V 1.0, we kind of like combined all of the capabilities that I mentioned earlier, and it's the first iteration of our thesis. So it's a collection of all these different domains that you see on the slide: robotics, gameplay, common sense reasoning, spatial reasoning, tool use, and object detection. So I'll get into the data sets that we used for V 1.0. So for each of these capabilities, as a first step, we select representative data sets that kind of like tackle each of these capabilities. So for continuous actions, we have the OpenX embodiment data, which we use for V 0.1. So we pick one data set from each morphology in the OpenX collection. So these are robots with bimanual embodiments, wheeled robots, single arm robots, quadrupedal robots. So this makes the action space very varied, even though they're all real world robotics data. And then for gameplay or discrete actions, we have Overcooked. So Overcooked is basically a multi-agent coordination game. Many of you might have even played it. It's available in a lot of consoles as well. So given a recipe, given a time constraint, uh, basically two players have to coordinate to complete a certain dish. And there's a lot of constraints in the game as well. And so when you have, similar to ProcGen, when you have expert trajectories of the actions, you have a ground truth data set for this. And then for common sense reasoning, we use Pika, which is physical question answering. And so these are questions about actions in the real world. And this is something that typically pre-training takes care of in most models. And then for spatial reasoning, we use this data set called Squad. So Squad basically has 3D polygon scans from the ScanNet data set. So these are scans of different rooms, and they're questions that are based on the spatial dynamics of a scan of a given room. So an example could be if there's a whiteboard and a table and a bunch of chairs, the question could be next to the chair, is there a whiteboard? Or like next to the whiteboard, how many chairs are present? So this kind of like requires whatever agent is being tested to understand the spatial scene, right? And then for object detection, we use this data set called ODNW. We had to ODNW is object detection in the wild. We kind of had to repurpose this data set because originally ODNW is a bounding box prediction data set. So given a scene in the wild, the model is asked to predict the bounding box for a given object. But VLAs, VLMs, out of the box are not able to produce bounding box coordinates until they've been fine-tuned on something like that. And so what we did was we used the ground truth bounding box coordinates and kind of cropped out the objects of interest and made it a classification task instead. Yeah, and then for tool use, we use Berkeley's function calling dataset, specifically the multi-turn conversation dataset. So this is basically given a multi-turn conversation, the agent is asked, the agent or the model, whatever is being tested, needs to call the appropriate tools to complete the requests of the user during this conversation. So, for example, like booking a flight or booking a hotel room, you need to use, a web search tool, a booking API, stuff like that. So this is what we had, and a lot of these data sets needed processing or some sort of like repurposing or transformation for them to be used as eval data sets. I'll kind of get into that in a bit as well. And yeah, the models we profiled for V 1.0, as I mentioned earlier, basically these three different categories. So vision language models. So state-of-the-art model was GPT-5 with reasoning. And for VLAs, we used the Pi0 model from physical intelligence. So just to give a brief about what VLAs are, they're usually VLMs that are fine-tuned or co-trained on robotics tasks. There are various different methods to approach this. And this is one of the probably the most popular direction right now in fine-tuning VLMs on a completely different domain, which is robotics in this case. So there are various different methods where you can create these VLAs. So you either use the token space of the VLM itself and kind of allocate a part of the token space for action tokens in robotics and then fine-tune it, or else you have a separate action head, which is basically trained to kind of like produce continuous action trajectories. And Pi0 is follows the latter. It uses a polygemma backbone and has an action head that's trained using flow matching. And so given a robotic scene, it's able to produce a chunk of actions, a trajectory of actions of what needs to be done given a certain goal, right? And then there's the third category, which is the generalist model. And the state-of-the-art model in this category that we picked was Microsoft's Magma. And Magma is basically a model that's based on Llama 3, and it's been pre-trained on like a large amount of like vision language data sets, including images, videos, robotics data, and also a lot of actionable visual objects. So what does this mean? Like elements in a graphical user interface or tracking the object movements in a robotics data set. So they use these concepts of set of mark and trace of mark where they train the model to produce a set of coordinates in context of a given action, or either like just grounding the object or the motion of the object between scenes, right? And it claims to be state of the art on tasks like UI navigation, robot manipulation, and so yeah, it kind of like compares favorably on models that have been trained specifically for these domains as well. So these are kind of the three models that we picked to start off profiling on V1.0, and we have like more models that we will profile as well, but these are kind of like representative of the field right now. Cool. So I guess like diving deep into the specific methodology for the whole V1.0 effort, we kind of saw it as three different efforts. So one is obviously acquiring the data, processing it, creating, making them suitable for evaluation. And then two is adapting these models to data that is completely out of domain. And three is designing the right metrics and evaluation protocols to fairly assess how well these models do on data that is completely out of their domain, out of their like training distribution. Right. So for data acquisition, we do have like we completely open sourced our SDK that we use to download, translate, and utilize these data sets. So for OpenX, the main processing was we converted it to TensorFlow data sets, which makes it very easy to ingest, use, kind of like standardize the schema of the data as well. And I think for object detection in wild, ODNW, I mentioned how we repurposed the data from a bounding box coordination, a bounding box prediction data set to a classification data set. And then with Squad, because the scans are 3D polygon files, we kind of we converted it to 2D image to a 2D image data set because a polygon file can't be ingested by VLAs and VLMs of today. So we take the kind of like the top-down view of a 3D scan of a room, take a screenshot of that, and that becomes our observation for a given time step. So it becomes a 2D image file. And then for Overcooked, we use the state information in the expert trajectories to kind of render the visual observations for each time step. So if you missed it, like the last row are basically images of overcooked time steps. So that's how like the state looks when it's rendered into an image. And then and then obviously we created eval splits, and we don't release these eval splits just to avoid contamination. But when you submit your model to be evaluated on our data sets on our benchmark, they will be inference will be run on these eval splits. Yeah, and so the model adaptations direction is very interesting because a model like GPT-5 can't really produce continuous action trajectories. A model like Pi0, which has been trained to produce continuous action trajectories, cannot generate language that's required for these vision language data sets. So a lot of effort goes into adapting these. But during the process, I think we also realized how much the architecture and training methodologies of all these state-of-the-art models kind of limits them from being truly generalizable. And so for the VLM adaptation, we basically created this framework called Genesis, and it adapts VLMs to new domains, specifically actions in our case, because that's what we wanted it for. So for Overcooked and OpenX, GPT will now produce continuous actions or discrete actions based on this framework. And then for Pi0, because it has this action head that purely only outputs continuous action trajectories, we needed to find a way to adapt it to produce language. And so for this, what we did was because Pi0 is completely open source, the weights are open as well. We extracted the backbone polygemma weights from Pi0's entire like weight dictionary, because the polygemma part of the weights is what is responsible for the vision language understanding. And we kind of inject this into a Hugging Face polygemma backbone so that we can like utilize the native autoregression that the Hugging Face model has in their generate function. And we test these kind of like Pi0 fine-tuned polygemma weights on vision language datasets. So that's how we got that's how we were able to evaluate a model like Pi0 on vision language. And then for Magma, we needed minimal processing and adaptation because it is supposed to be a model that can do all of these different tasks across all these domains. The only pre-processing we had to do was so Magma architecturally can only produce actions in robotics of 7 dimensions. So it can only do, so which means that it was only trained on embodiments that had 7 degrees of freedom. So typically this is your XYZ coordinates, the roll, pitch, yaw of an arm, and then the gripper action. However, because we picked many different embodiments from the OpenX dataset, like a bimanual robot, which has 2 arms, a wheeled robot, which basically just has 2 dimensions in its action space, or a quadrupedal, which has 12. We had to find a way to, allow Magma to kind of like produce actions corresponding to this space. And for that, luckily enough, I think the authors in their original work have ways to process these action spaces to kind of convert them to seven-dimensional action spaces. And so we used that, we transformed the data and made it suitable for Magma to infer. But then I think for quadrupedal, the original work did not have any information. So we kind of basically used the same Genesis framework that we use for GPT-5 and adapted Magma to do this specific inference on OpenX quadrupedal Genesis style. So like a vision language model, basically. So tapping into its vision language capabilities. So we found ways to zero shot evaluate all these state-of-the-art models on data sets that are completely out of their distribution and they're architecturally not able to infer on originally. And then the third effort, I think, is important. It's designing the right metrics and the evaluation protocols to understand how well these models do on data that's out of their distribution. So for discrete action spaces, it was pretty simple. We could use the usual precision recall F1 and also the Breyer mean absolute errors, which I mentioned earlier, which basically assesses uh, how confident the model is in predicting a certain action class. So the MAE is based on the probabilities instead of the prediction itself. And then for continuous action spaces, we use a normalized mean absolute error between the ground truth action and the predicted action. And we have different variations of this mean absolute error. So we have quantile filtered MAE values and MAEs beyond thresholds just to understand the effects of outliers. And they're normalized with respect to like kind of a naive baseline mean predictor so that you can do cross model comparisons and also comparison across data sets. Um, and then for tool use, we basically just used accuracy because for something like, so in Berkeley function calling, it's purely a function calling data set. And the only way you can, like use the tool correctly is if you get the function signature perfectly correct. So the name has to be correct, the parameters have to be correct, the order of the parameters in the function have to be correct. So we go with an accuracy metric, but we also have variations because it's a multi-turn conversation data set. So we have turn level accuracies and conversation level accuracies, and then a data set wide accuracy as well. And then for language generation, like Squad, for example, where the output is either a word or a phrase or a sentence, we use an exact match rate, which is a very harsh metric. So it kind of like understands how well the model is at getting the answer exactly right. But we also do use similarity scores, which kind of gives you an idea of how close these models are to the right answer in a free flow language generation data set. And then for classification, it's the usual precision recall F1 metrics. And then for the MCQ data sets like Pika, it's just purely accuracy because there's only one correct answer. So this is kind of like an overview of like our entire process, the things we did for V1.0 to create this benchmark, to obtain our results and everything that you see on our website. Yeah, so I think the interesting part is are the results from this effort. So I'll first start with some of the bigger surprising results and then move on to all the other metrics that we calculated as well. So one thing that we observed, which was very interesting, was that Pi0, which is a state-of-the-art vision language action model, completely collapses on vision language tasks in general. So on the slide, you basically see an example of the ODNW, the object detection dataset. And so Pi0, the way it was evaluated was, like I mentioned, we take the polygemma weights, put it into a skeleton polygemma hugging face model, and generate. And you notice that it basically spits out gibberish. It has this like sort of like a it's we hypothesized that this increa token, which kind of repeats, is like an end of sequence token probably in robotics. Well, what's more interesting is that there's like catastrophic forgetting of its backbone capabilities. So Pi0 is a model that is based on a vision language model. But after like just naive fine tuning on robotics, it just completely collapses in a different domain, like language generation. And so this is kind of very interesting. It shows that domain specific fine tuning without any particular methods of knowledge insulation or preservation of the backbone knowledge just doesn't work out of the box. And so, yeah, this was one of our main results. And then another interesting result we saw with Magma was that there was a complete corruption in the output space. So I think, like I mentioned, Magma was trained on the set of mark and trace of mark data, which basically is coordinates for grounding a certain visual element or tracking its movement between scenes. And so one interesting thing that we saw is that, again, when you evaluate it on a data set like ODNW or its classification, we saw this across multiple different vision language data sets in our collection as well, is that it randomly just produces these coordinates, which have nothing to do with the data set at all. So these are completely invalid outputs. So Magma also had a very high rate of invalid outputs, not as much as Pi0, because obviously Pi0 could barely produce English as well. But yeah, so this is very interesting that there's complete corruption in the output space. And then another thing that we observed, kind of similar to the V0.2 result on the ProcGen data, was that GPT-5 and Pi0 collapse on these discrete action datasets like Overcooked. In this particular example, Pi0 collapses on the actions 25 and 26, which map to the cook one or player one staying in the same position, player two going south, or the player one staying in player two going east. So it's kind of very evident that there is no real understanding of how to complete this specific action in a completely new domain for a model like Pi0 or GPT-5 even. And some other results, these are more like expected results, so I'll kind of like go through them quickly. Pika is just a language-based data set, so obviously GPT-5 does really well, and Magma, as expected, kind of like is the middle ground between Pi0 and GPT-5, and Pi0 can barely produce language, so it does really bad. And then these are the language generation datasets, Squad and RoboVQA. RoboVQA is basically a part of OpenX, but instead of continuous actions being the answer for each sample, it's visual question answers based on a robotic scene. So it's very similar to Squad in terms of what the questions are, the answers are, and RoboVQA is robotics, and Squad is just 3D scans of a given room. And you see again that Magma is kind of like the middle ground between Pi0 and GPT-5, but even Magma does really bad because in some of these cases, it triggers the coordinate outputs, which is completely wrong. Yeah. And then on the object detection dataset, GPT-5 does really well. Magma shows a high variance between the different sub-data sets of ODNW. It has all these different subcategories. Pi0, again, cannot do these tasks because it just doesn't produce a valid output. And then Overcooked, like the action data sets in general, these models find it very hard to perform well on. So Overcooked, if you look at the recall, even though GPT-5 is better than Pi0 and Magma, the overall scores is still very bad, not even a 4% macro recall. And if you look at something like OpenX, the interesting thing is that GPT-5 performs better than Pi0 and Magma on almost all of these embodiments, which is very interesting because Pi0 and Magma are the two models that have been trained on robotics, and GPT-5 hasn't. But that doesn't say much because, again, all three of them are just really bad at this task in general. And they just have very poor generalizability to a complex task such as robotics or multi-agent coordination in discrete action spaces. So large generalizability gap. And yeah, tool use, they're also very poor in performance. Pi0 can produce a single correct answer, and Magma has like maybe, I guess, like 2 or 3 turns correct. We don't have the GPT-5 score in this graph because GPT-5 was officially reported on the BFCL leaderboard, and I think it does decently around maybe like 30 to 40%. So we didn't have to profile it again. The results are already on their leaderboard. Yeah, so what does this mean? Like, what are like some key takeaways from all these different results that you saw? So definitely, it seems like there's no generalization free lunch. Like, however, the state-of-the-art models today are architected, trained, fine-tuned, they just cannot out of the box work on these completely new domains that are out of their training distribution. And two is even after fine tuning, if you use a vanilla fine tuning method like how Pi0 does, where you have a VLM backbone and you fine tune this action head to produce continuous actions, it corrupts the vision language understanding and generation capabilities, right? And the third that we saw in Magma was that the output space corruption follows a very predictable pattern, and it's an inherent issue in its training methodology because we experimented with a bunch of prompts, and it's not a simple issue that really sophisticated prompt engineering can just solve right out of the box. And yeah, like I mentioned with Magma, I think it can only predict actions that are 7 dimensions for robotics. And so a lot of these models just architecturally are very constrained and are unable to generalize to even within their domain slightly out of distribution. So even if you go to a different morphology or embodiment of robots, Magma is going to fail miserably, which we saw. So there's clear like issues at the architectural and training level as well to generalization. Yeah. So, okay, now given all of this, I guess V 1.0's results and the way we think about the next generation of multimodal models or systems kind of informed us and has been informing us on how we think about the future of AI benchmarks as well. So I've kind of like categorized it into a few different prongs. And so the first one is we need live contamination-free benchmarks. So LiveBench is a good example of this. It already exists, and they have, I think, periods over which they basically overhaul their benchmarks so that it's after the cutoff of state-of-the-art models, and they're keeping it contamination-free, and it's not prone to being trained on by the models. And I think like this is definitely the future because uh, right now benchmarks are when they're like nearly saturated and completely contaminated, uh, they kind of become participation trophies instead of benchmarks, and you're just reporting on scores that are like 2% more than the previous state of the art. But in reality, they're very like they're very incapable of doing well in the real world. So this is an important direction for AI benchmarks. And two is drawing inspiration from how the original ProcGen environment was constructed by OpenAI. I think procedurally increasing in difficulty is a very important characteristic for benchmarks because they prevent saturation. So I think Arc AGI does this, but they do it over like longer horizons where when one version of the benchmark is nearly saturated, they come out with a much more challenging version of the same benchmark, right? So if you can find ways to tune up versions of your benchmark to make it procedurally hard in kind of like non-deterministic ways, you're preventing saturation, which is a very important problem today. And three, I think like we have been exploring this idea of simulated environments as benchmarks. And I think this is very important because simulated environments will offer you the highest fidelity transfer to the real world, right? It's the most representative of what a scenario in the real world could look like. And it could be for robotics, it could be for computer use, and you have control over these environments. So you could actually do the previous two prongs that I mentioned. Because it's a simulated environment, it's going to be contamination free. And two, because you have control over creating this environment, you could make it procedurally increasing in difficulty as well. And I think this is much more representative of when you evaluate a model on a simulated environment as a benchmark, it's going to be much more reliable when you use it in the real world in production. And then three is evaluation. I mean, four is evaluation and production. This image here is basically an example of how Discord uses their AI content moderation model and evaluate that in production. So basically, this becoming good at this, becoming good at evaluating in production is going to enable like this like longer term goal of continual learning, where all of these models basically each failure becomes like sort of like a future test case. Each interaction in production becomes a data point that you can train on further, and it kind of creates this flywheel where even if models today are bad, you know how exactly they're bad in production and in a real world use case, and kind of make them continually better. And then finally, I think the limit of how we see benchmarks. This is kind of the limit of simulated environments as well, are these world models. So you see a lot of news and research now about these world models from companies like DeepMind, World Labs. So basically, with the simulation environment, you have a set of rules, and you kind of like create this prototype representation of the real world. But with world models, it's something much more nuanced, where you're basically modeling the physics of the environment where you want to like evaluate these models, right? So if you can have these worlds that are procedurally generated, increasing in complexity, very reliably model the physics of environments like robotics or computer use or gameplay, uh, you're basically almost like evaluating it in production because this is a very good representation of what production looks like. And so, yeah, I think at the limit of it, we look at it as world models, which are really good causal reasoners. It also like helps you get beyond offline trajectories, because with offline trajectories, you're comparing models based on a given set of ground truth action trajectories. But in reality, models or systems can take you know so many different trajectories to achieve this final goal. And when you have something like a world model that models the underlying physics, no matter what action the agent or model takes, you always have a response state or a next state that you get. And you have a much more nuanced way to evaluate these models. So yeah, so that's it for MultiNet V 1.0, how we think about this next generation of models and benchmarks and how we want the future of AI benchmarks to go. If you guys find this interesting, I do want to mention first that obviously couldn't have done this without my team. A big shout out to Dip, Harsh, Helen, Mridul, Sean, Aryan, Harry, and Locke. I think we spent the last few weeks, months working on these problems, and we have a research paper coming out soon. And we presented earlier this year at ICML as well. So it's been good sharing this research, and the team has been doing great work. So shout out to them. And if you guys are interested in joining this effort and working in kind of like a part-time capacity on the open source parts of it, definitely check out the opportunities in the Manifold website. And if you're interested in working on it full time, scaling up these models and benchmarks that we talked about, these models of the future, definitely consider joining Fig and reach out to us if you're interested. Feel free to reach out to me or Harsh, and we'll be happy to chat with you. And yeah, I think that's it I had. So, Sid, I guess if you want to open it up to
Yeah,
questions.
Pranav, thank you for the excellent talk. Great work. I am now going to allow people to unmute. If you have a question, please use the emoji and raise your hand or speak one at a time. That should work itself out though. Feel free to ask. We have a few questions in the chat also.
Hello,
Hey,
I'm the one in the chat. I was saying that you were talking about how that model contamination of the test benchmarks is a major problem. And I was wondering, so you're saying, of course, that you're not going to leak that data so that that doesn't get trained on, but how does that solve, say, example, the problem of like actually having other people come in and test your benchmark? Like, for example, what if it was like a company that has a famous benchmark and we don't trust that they're being equal to all models? Like, for example, they're having their own model. How does that work out?
so do you mean so I guess like the way we solve like the whole contamination issue is that we kind of like maintain the eval splits ourselves, and when a model or a system or like any model provider submits their models, we have an evaluation harness which kind of like runs. We give them a good idea of how our evaluation harness is, how exactly it works, and we kind of have the results for that, and we just like offer them the results. And I think different benchmarks do this in different ways. I think SweBench has a verification process, so you have a SweBench verified versus a SweBench where you just run the evaluation harness on your own and upload results. Not sure if I answered your question, but yeah, I guess like the way we avoid contamination is that we keep the eval splits to ourselves, run the evaluations ourselves, and just publish the results, as opposed to completely providing the eval data open source.
So maybe I could chime in. Michael,
Yeah.
I'm also one of the researchers who work on this. My name's Hirsch. So basically, it's a very good question, and I think it's very tricky. So one side of contamination prevention is this idea of continual updating. Okay, so but I think Pranav has discussed that, and we put that to one side. Um, the idea of who owns the eval process and how do you mitigate bias? So I'm not a decentralization expert. It's funny, one of the audience members also reached out over another channel asking about potential avenues of like introducing some sort of like decentralized guarantees here, and maybe some cryptographic guarantees. But I think the sort of like logistics approach here is that so Manifold is a fully independent research group, and it's a nonprofit, and we work. So we are explicitly trying to set up a benchmarking initiative with several universities, and so this is already underway. We haven't announced it yet, but the idea is that we work with like groups like MIT. A lot of this research was done with research groups at MIT, Georgia Tech, and Tufts, and so we will have a consortium of several. Uh, Partners who the idea is that everybody in this is a nonprofit and they're all incentivized to collectively make sure that this is run sort of appropriately so that no single company is biasing this. A lot of these research projects will get sponsorships and grants, et cetera, from different companies that may have certain motivations. But the idea is that if we have enough votes, then hopefully there's no bias, and we want all of our short of the actual eval data itself, which um, maybe the solution is sort of a private test set, public test set kind of thing, the way that ArcAGI, et cetera, do it. Beyond that, we hope to just basically build credibility and trust through everything being open and everybody being an open source partner. Um, the next step is interesting. I haven't thought through how we can enforce more rigorous guarantees there, and I think that'd be a really interesting discussion to engage in, and would love to hear thoughts and suggestions from the community, both here and or in our Discord or anywhere else. So, it's a great question and something we're like constantly trying to navigate. But I can say, I guess, that everything from our entire roadmap, all the issues, et cetera, is open source, and so we hope that uh, it's the kind of thing that we can build trust with the community and have enough larger sort of open science focused players involved that there's we mitigate the likelihood that there's a lot of bias from some single sponsoring agency, and we will refuse it. I mean, we've turned down lots of uh, larger scale sponsorships explicitly because of those reasons. We're very focused on open science, so not the most rigorous answer, but it's an evolving process.
Yeah, it looks like you've at least addressed the problem and are looking to solutions. So I think that answers my question. Thanks.
Great. Yeah, thank you.
If anybody else has any other questions, feel free to chime in. If not, I have a quick question about the process. I'll just go ahead and ask it. So, yeah, I think as far as I understand and from this talk, one of the major pieces of this project was this sort of conversion process where, like the Genesis framework or the process you described for Pi Zero, the team has to think about a way to adapt one model which is not trained to act out of distribution, right, and test its generalization performance. But that kind of begs the question, the zero-shot generalization performance then is somewhat dependent on the process that the team used to test it, right? Um, I guess, yeah, my first question is that true, or is there something more fundamental that I'm missing where the model would perform the same under different sort of generalization processes?
No, that's definitely true. So I
Okay.
think like for us, the way we did it was the most fair and like lowest hanging adaptation for zero shot evals, right? Because I think our goal with this benchmark is not to ensure that GPT-5 does the best possible way it can on this like completely out of distribution domain, because we eventually want to like evolve, and we are evolving into this benchmark where instead of us profiling, we have a lot of model providers and teams submitting their models and systems, and so they have the freedom to adapt it however they like. And we through our evaluation harness and submission software, we basically provide them some public samples that are not part of the eval split, which helps them, they get an idea of how they can adapt their models and systems to work on this kind of data, output formats, input formats. And then, yeah, they basically submit an adapted model. Or if they've built a model that works on all of these, they just submit their model and we only run the evaluation process and give them the results. So yeah, so I think also like another like key point here is that the fact that these models even need a like a very sophisticated adaptation process to work on these different domains shows kind of like an inherent inability to generalize. Yeah, and we do also want to move into like fine-tuned based evaluations. And so as we go into more of these sophisticated evals, it's totally up to the model providers to adapt it the way they want. Yeah.
Yeah, actually, that's also a good thing in a sense for the future benchmarks, like you were mentioning, because that'll create this competitive effect where people who worked on the model, they need to
Yep.
adapt it as well as they can, right? And there'll be like this competitive sort of selective effect, which is a good thing. That makes sense.
Yeah, and I think like the hope is also that people eventually build models that are truly generalizable and they move towards this like next generation of multimodal models that we're talking about. So the idea is they build architectures that are more conducive to generalization, training methodologies, fine-tuning methods. So yeah, I think that's the goal. Yep.
Definitely, definitely. Thank you. Any other questions, folks?
I think that might be it.
Okay, excellent. Well, Pranav, once again, thank you for giving this excellent talk, and thank you to the MultiNet team for working on this release. This is a big one. Um, and thank you everybody for attending today's talk. If you like talks like this is our Frontiers event series. Like I mentioned at the beginning, this is a series where we give researchers the chance to talk about cutting edge topics that they're working on and do deep dives into how they work. Of course, the organization that is hosting this, we're Manifold Research. We're working on paradigm-changing technology research in the open. This includes things like artificial intelligence, space robotics, swarm systems, etc. If you have any questions about anything, feel free to ask us in the Discord, and you can see future events as well. on our website at manifoldrg.com/events. Any relevant links and slides will be shared shortly in the Discord after the talk. Once again, everybody, thank you so much for joining us today, and we hope to see you at the next one. Thank you, Pranav.
Thanks, everyone.
Thanks, Pranav.